So my name is Michael Kennedy. Thanks for coming to my talk today. I have 2 sessions on MongoDB. This is sort of like a slightly advanced topic. Tomorrow we'll have the introductory one. So if this is interesting, come to the introductory one if you haven't done it before. Let's start by just having like a quick conversation. And by the way, when I'm up here talking, if you have a question, please ask it. Don't wait till the end. So how many of you guys are using some sort of NoSQL database? A couple of you. What ones?
We've got Mongo, Elasticsearch, Neo.
Nice, you guys are doing a bunch.
Yeah, various different bits and pieces. So yeah, those two are Elasticsearch and Mongo.
Okay, yeah.
We have Redis as well.
So, do you use that mostly for caching or?
Yeah.
Yeah. Okay. Sweet. And you?
It's 2.6 version. MongoDB
Yeah.
at this moment, but previously my project Breakout. But I don't remember what kind of version it was.
Yeah. Okay. Cool. And then someone else.
I use Mongo.
Mongo as well. Okay. Right on. Okay. So we're going to talk about Mongo in this one. We'll talk a little bit generally about sort of NoSQL in the beginning, and then we'll focus on Mongo as we kind of get into it. Okay. So the first thing I want to talk about is sort of what is NoSQL, because we're going to look at a couple of different types of NoSQL databases, and then we're going to focus in on the document databases that some of you are familiar with. So if you look at the history of the term NoSQL, it actually goes back to a Twitter hashtag. So in June 11th, 2009, there was this meetup that was formed by this guy, I can't remember his first name, Johan or something like that, from Last FM in San Francisco. And he was getting together with a bunch of people from the various startups that were doing sort of web scale type of stuff. And somebody was like, hey, we need a term for this get together. They were getting together to talk about databases and how do we take what you think of as like regular relational databases and put them on clusters in some way that we can horizontally scale them without too much work, right? So they were talking about new types of databases, and, things like Cassandra and Redis, all those types of things. So somebody came up with this term #NoSQL so they could use it on Twitter, and that's basically where the definition comes from. A lot of people will tell you NoSQL means not only SQL. It's kind of like an apologetic, hey, can't we be all friends? Like, it's a fine worldview, but it's not where this comes from, right? It comes from these guys trying to do sort of horizontal scaling of databases. So in my world, I'd say like, what you're talking about is these are database systems that are cluster friendly generally, and they more or less trade inter-entity relationships like joins and foreign keys and stuff in order to more easily horizontally scale, okay? So there's often what are described as 4 types of NoSQL databases, although under my definition only 3 of them really land there. We've got at the sort of high end of performance and easy scale, but low end of usability and usefulness are these key value stores. So things like Amazon DynamoDB or Rake or so on, that's one end. Maybe at the other end we have these graph databases that not only store the entities, but store the pre-computed relationships. So instead of having a table and a foreign key relationship that's computed at runtime, like it literally writes the traversal of the relationship down. So that's very neat. We also have these sort of semi-SQL relational-like things, column-oriented databases, and then probably the most popular type, which includes Mongo and Raven, which you guys talked about, are the document databases. Okay. So if you see like how do we store the data for a key value store, basically you've got a primary key and you've got some opaque thing to the database that it's going to store. Right? So this stuff is crazy easy to horizontally scale because you can only ask for something by primary key and there's no relationships between anything, so that's really easy to just sort of fan out, right? But querying it becomes super hard. Like what if you somehow in here store this hierarchy of like orders and customers and stuff? You want to say what's the average price of the order? Well, how do you do that, right? Or give me the orders for today. That gets to be really hard. Column-oriented databases are kind of funky. They can store stuff that looks like regular databases, tabular stuff, and then they can also store kind of like a pre-computed join relationships here. So here I've got like sort of columns and then a set of orders that are also stored into like a single record, effectively. Then we have graph databases, and graph databases store both the relationships and the entities. So we were talking about my friend Pierre. He owns an electric bike. We talked a lot about electric stuff, so I started thinking about Teslas and Volts. You can just sort of traverse these relationships super easy. Do you guys think that's easy to scale or horizontally scale? No, that's worse than a relational database to scale, right? Because everything is related, and it's the relationships that cause like inter-machine communications and all that sort of overhead, right? So that's not super friendly. And the thing I want to talk a lot about is the document databases, right? So some of what I'm going to tell you applies generally to things like CouchDB, RavenDB, and so on. Some of it's specific to Mongo. But they all store their data in this format, right? So we've got things that would look like a regular database. So these would be like the columns. We've got a primary key, which is the ID, a name, an active course. This is actually right out of the development or course catalog. We use MongoDB for our website. And this happens to be our extensive C++ class I grabbed. And so this looks like normal stuff. But this, not so much like a sort of a square tabular database, right? What's the angle bracket in JavaScript mean? Or JSON rather? Array. And what about the curly brace? Object. So here we have actually an array of like sub-objects. So in a normal database, this would be a second table, and there would be some kind of foreign key relationship and a join to get these. But in MongoDB or the other document databases, you can kind of think of these entities as being pre-joined. So this one record contains not just the class information, but the events that we're running where you might come to a class on this place, this location, on this date, something like that. So this becomes super easy to horizontally scale if everything you care about is contained within that one record. Right? Because if I take this and put one of them on that machine and take another record and put it on that machine, if I can pull this one back, and I know about the engagements, and I don't really care about other relationships, this is super easy to horizontally scale. Right? So that's one of the real values of these document databases, is you can design your entities in a way that if you pull one record back, usually, like 80, 90% of the time, that's the only query or database interaction you need, because it's got everything you need. We'll talk about setting up machines to do the other types of scaling. Okay, so these all sound really different, but they're not so different, actually. The document databases, the column-oriented databases, and even the key value stores all kind of work in more or less the same way. They've got like these kind of natural aggregates. You know, if you think of like Eric Evans' domain-driven design type of database theory, these are sort of, there's this top-level thing that's kind of in charge of its sub-pieces, right? And those are really interesting for horizontal scaling because you can put them in different places, and generally they have enough information to be useful by themselves. Relational databases, not so aggregate. Graph databases, millions of broken, shattered pieces, right? Not so much. So in my world, NoSQL lands like here. The graph databases aren't part of this thing. The people who say NoSQL means not only SQL, well then obviously it's in there. All right, so let's look at a couple of real world examples. And then I'm gonna show you some examples that might be out of reach of what you're normally trying to do, but maybe will inspire you, okay? So what I'm gonna show you here, everybody would find this to be useful and so on, right? No matter how much data you have. So we've got, let me just pull it up here. We have this place, online training place called Learning Line. Let me pull up a class here. And we originally wrote this this website in any framework. I think we were using SQL Azure or something like that. And here's a very common page. Like people might want to come and do this lesson here. And if you just think about all the various moving parts that are required to show this one page, you've got the tags here that are about this, what we call a task. You've got who it was written by, who it was reviewed by. You've got the votes on it. You've got the prerequisites. You've got the successor pieces. If you scroll down here, you've got the parts of the lesson, how long those all are, the types of them. Like the number of joins we had to do to show just a simple page, even like this, was kind of ridiculous. These are all the tables that are involved. That was a 17-way join to show that table, to show that page. That was wrong. It wasn't good. Now, you could do caching, right? You could do Redis or something like that, and it put some sort of cache in front of it. But now you're maintaining like basically two data layers, and like every now and then one gets out of sync with the other. You're like, oh man, I've got to change this, I've got to flush the cache when we do this. And it's just complexity that you have to add to make things go really smooth. So here's how this looks in a relational database. Want to see how it looks in MongoDB or in document database? Those are the tables. This one we typically don't access. This one we access at the beginning of every page request, regardless of what page it is, just so we know if they're authenticated or not. And now we have that one query. So our database time went from, maybe a couple hundred milliseconds or half a second or something silly like that, down to 1 to 2 milliseconds database time to process that page. And it became easier to understand. Like, this is super easy to understand. I'll show you a better picture of it in a minute. This is not super easy to understand. Right? We've gotten used to it, right? It's like, this is the kind of world you have to live in. You're a programmer, you have databases. They've got all these lines and they get so dense and small you don't know what they mean anymore, but it's really important to do this third normal form thing, so we do this, right? But you don't have to, like document databases give you all this flexibility. So if you go in here, break this apart, this is what it really looks like. And the gray boxes are the actual tables, or what's called collections, because they're non-tabular in document databases. Right, so here with this top thing, and inside of it has an array of activities. The array of activities makes one of these, and it has an array of votes, and all these things, right? So now if I want to get one of these back, I just go, boom, give me the one I need, and it's already got everything I need to show. That's great, okay. So let's look at one thing really quick before we move on. So this is all, it could be one machine, it could be 100 machines. It has nothing to do with clusters. Let me show you another simple example here. So I'm going to use this program called RoboMongo. And RoboMongo works on all the different platforms that you care about. Windows, Linux, and OS X. So over here, let's go to this little books collection database and go to this book collection. So let me do this so you guys can see a little better. All right, so we can look at it in various forms here. You can see, okay, we have this set of books, all right? And some of this stuff is like regular, sort of tabular type stuff, right? These are the primary values, but then also you've got, let's go to this one that might have more ratings. Whoop. Yeah, so then we've got an array of sub-objects, which are user ratings with the user ID and a value. So the person hated that book, this person loved that book, and so on, okay? So what's interesting about this? Well, let me show you one more view really quick, because I know this is new to some of you guys. So here's the JSON representation. It's stored in a binary form. It's not actually text, but it's something called BSON, a binary version of JSON. So here's the thing that's interesting. In here, we have 271,000 books. Within those books, in that nested array, like you can think of this as a join or related table or something like that, we have 1.2 million reviews of these books. And if, a lot of times people will say to me, like, Michael, this is kind of cool, but we can do that in SQL Server. I'm like, oh yeah, how can you do this in SQL Server? Like, we could put XML in there. Oh yeah, can you query into the XML with indexes? No. So let's go over here. Let me find this one. Let's find some dude who reviewed something, or dudette. I'm not. Copy value. What I want to do is I want to write a query. Now the query syntax, if you've never seen this stuff before, it may send you running that direction, or that way the door is open back there. But if you really program against it, it's probably LINQ, right? So think of this as a LINQ query that gets transformed into this query language. So I can come in here and I can say, I would like to go to these objects, to these books. I would like to go to their rating section. And within the rating section, I would like to look for the user ID. So there's this JavaScript sort of prototypical language that you can use. So I can say, I want to go to the ratings collection and find the user ID that is equal to this value. Okay, 271,000 books. Within those things, sort of sprinkled through, 1.2 million records. How long will this query take? Half a minute? A second? Who thinks it'll be faster than half a second? Yeah? The guys who are using MongoDB, their hands go straight up. How many think it'll be faster than 20 milliseconds? Mark, no, there's not many hands up. How many think it'll be faster than 2 milliseconds? right? Like, these are questions that would be ridiculous to ask about like a relational database. If I'm doing a join of these tables and then like 2 milliseconds, like, no. All right, okay, so let's run it. The very first time the index is cold on disk and it takes 42 milliseconds. You run it again, it takes less than a millisecond. I could change it, just the index had to come off disk, right? So it took, a couple of milliseconds. Right, so this is not horizontal scaling. This you can do on one machine, like I have just one machine here, right? There's no tricks. So you get this super, super fast stuff. And the reason this works is because I've set up an index into that subdocument there, right? So here's what we're gonna do. We're gonna take this sort of cool idea of nesting these things. We can still query them very fast. It's not like creating this hierarchical relationship kills the ability to query these things, which is maybe what people initially think. But it allows us to distribute them horizontally. All right, so most of the rest of the presentation will be like, well, now how do we take this to the next level? Okay. All right, so we're gonna use MongoDB. I think everybody who said they did anything with this said they did MongoDB rather than some other database for the most part. I'm just gonna let you guys see a little picture and then think about like what other type of NoSQL database should I be using, or is this maybe a good choice? So one of these databases, or one of these graphs representing a database is different than the others, all right? This is a little bit different than the others. And if you look at this one, that's MongoDB. And actually, I realize I have this is an older version of the slides. Let me just open this one over here. I'm gonna give you newer data. Where are we? 14. Don't know which one that one found. Sorry about that. So, the off the screen is sort of this one. Maybe I can scooch it. There we go. All right, so here's the newest data, right? And it's still, this is 2 more years of data. We were right here before. It still looks like that. Other people say you should use CouchDB because I don't know why they tell me that, but they do. This is CouchDB. It's going down. If you go and you're thinking about like something to bet your career on, and it's got this kind of graph, it's a bad choice, right? Think of something else. RavenDB doesn't even show up on here. It's like it's just on the 0 axis there, right? Moreover, the 2 other document databases, Raven and Couch, both have basically this ability to reasonably accept eventual consistency, right? If I do an insert and then immediately query it, you may or may not read what you wrote, depending on certain things. MongoDB is like SQL Server. If you write it and then you try to read it back, it comes back. It's strongly consistent. There's certain ways where you can add eventual consistency to get scale out, but by default, you don't have this sort of eventual consistency. So that's really nice. All right, so scaling out. We can basically scale out in 2 different ways in this system. One, you can scale out by kind of locating the same data in multiple places. Right? This might be some kind of geolocation thing. Like suppose you've got an Asia, a big set of users in Asia, and you've got a web tier in Asia, and you've got a bunch of users in America and a bunch of users in Europe. And you would like to somehow put your data near all of them, right, and keep them in sync. So we might be able to scale in that sense with replication. There's other things you can do with that as well. But the main thing that you would look at when you're doing like horizontal scaling and like kind of the reason that people met to talk about this NoSQL stuff in the first place is something called sharding. And now with sharding, what you do is you take your data and you put it into, you break it up into pieces. Like if I got my books, maybe I put 50,000 books in that machine and 50,000 books in that machine and so on, and break them up. You can do this with SQL Server. You just need a team and an application that understands the sharding scenario, right? I was on this sort of NoSQL versus SQL debate with the guy who was the former DBA for MySpace. I say MySpace. I didn't go out like, oh, MySpace. But at the time, MySpace was like the Facebook. Like they were huge for a while until they were not anymore. And they had 500 SQL servers. That's a lot of SQL servers. to do sharding and stuff on, and various ways of like locating parts of your data on different parts, and then having you go locate them. Well, there's no way to just like flip a switch in SQL Server and say, well, we need 500 and we want to scale horizontally. You got to go write your app to do that, right? With Mongo, you don't have to do anything in the app tier to do this scale, right? Just you set up your machine, your database servers differently, and now they do the scaling or they don't do the scale. Okay. With replication, you have to basically change your connection string if you want to get full advantage of it. But otherwise, this is not like part of your app, right? So you could add the scale out by like actually rewriting everything in almost any technology. But here you'll see that it's kind of automatic. Now, there's some really interesting use cases of MongoDB. And sort of one of them, one class of them, is this sort of set of companies that are doing database as a service with MongoDB. So there's three major ones. One is Object Rocket. One is something called MongoLab, and another is something called MongoHQ. And with all of them, kind of like SQL Azure, you can go and like buy like hosted, replicated stuff. I come over here. Let's see if I can find an interesting one for you. That's super how it does that. So Object Rocket, they were bought by Rackspace. This was started by a guy named Kenny Gorman. If you go look at their products, let's see. It'll show me price. Let's go look at pricing. So if you go over here and you pay like $150, they'll give you like automatically with you out doing any work. They'll give you 5 shards. They'll give you within each sharded piece. They'll give you a bunch of replication. They'll give you SSD, they'll give you automatic backups, right? So they'll do all this sort of stuff. So from one of these companies, let me let this get back up there. So from one of these companies, they passed around some stats and said, hey, we're looking to hire anybody who wants to come do MongoDB stuff with us, you know, please send us a resume. And by the way, just to give you a sense of the kind of cool things we're doing, we have just one customer that is doing some serious work. They have a single app that is doing 120,000 CRUD operations per second. And within that cluster, the cluster is communicating over to the app tier. And between the app tier and the cluster, it's over 2 gigs a second of data exchange. That's an insane amount of data, right? And your app doesn't even have to know about this. Like this app that could be consuming this could be just as stupid as like the thing the guy created in the garage, right? I mean, it's highly unlikely. But they didn't have to do anything in the app tier to get this kind of performance, right? They just configured their Mongo cluster. Okay, so how do we normally do scaling? Well, it normally looks like this, right? We normally get a small thing, and then we say, oh, that's not fast enough. And so we're like, all right, let's get some SSDs. Let's get as much RAM as will fit in the box. You know, let's get as many processors as we can, and we'll try to scale it up as much as you can. Because with relational databases, as soon as you try to put them in different places, either that's like basically impossible, or your app has to do it manually, right? Like, they're not built for that. So you scale up as high as you can, and there's, you know, you can get pretty big machines these days, especially if you go into EC2, as you'll see. But there are limits to what you can do here, right? And it's expensive, especially if it's in your own data set. Well, it's expensive either way. However, if we could use a bunch of cheap pizza boxes, right? If we could use like the $20 a month sort of EC2 machines, but we had 200 of them, and we could put a little bit of our data on each one, we could scale that out a lot more. I think Facebook, for one of their series of databases, they've got 2,700 little pieces, little servers, all involved in like one database. So the NoSQL databases, the things that are built to at least tolerate, if not embrace horizontal scaling, let you scale this way. This way is way more cloud friendly, it's cheaper, it's better for fault tolerance, all of these types of things, right? So it's really the fact that you're using things that are aggregate, that you don't have a lot of relationships between documents. And you might think, you know, if this is new to you guys, when you first hear that, well, I have to have relationships in my document. I have to have relationships. Like, this is a database. Data is related. That's true. But most of those relationships can be baked within a single document, so you don't have to cross outside other documents to get that relationship. You still can, we'll see, but the less you do that, the more it scales horizontally. Okay, so let's talk about sort of the difference between these two. We've got replication, which typically is not used for scaling, but you'll see has some really interesting possibilities there. Like I said, the geolocation is one of them. But if you're generally trying to do scaling horizontally across those different machines, your best bet is to do what's called sharding. All right, here's a picture I tried to draw to sort of represent what's happening. We've got our whole database, which we're represented by pieces of data or kind of labeled A, B, C, D, E. And in replication, the way it works is you have a bunch of servers, and on those servers, they each have a copy of the data. Okay. So there's interesting things you can do, like you could put server 3 next to you, in your region, and server 2 is maybe in some other region, and direct people to talk to those servers. Okay. You'll see there's some limitations to that. But if I had a lot of data, suppose I had a terabyte of data, could I put that onto a single machine and get reasonable performance out of it? Maybe if it was huge, right? But there's some limit where the data is too big to fit on just one machine. So you need to scale it out at some point, right? So this is where we started talking about, breaking stuff up into different network clusters and different machines and so on. And not everybody has this problem. So I just want to point out, first of all, there are other techniques which we can go into to try to make your app faster on a single server before you're like, oh, let's throw 10 related machines together that just add so much complexity. But if you've tried things like doing the right indexes and document design and so on, this is probably your best bet for scale out. Okay. So we'll come back to this picture. So first let's talk about sharding. So sharding is pretty easy to set up. You basically start up a bunch of machines and give them a few commands through this terminal that basically links them together. And then you set up one thing that's called a MongoS for a shard server. And then the real database I'll refer to as MongoD, not D for database, D for daemon, because it's a Linux thing from the beginning when they first came up with it. Works on Windows now, but the name is there. So the MongoS, the shard server, implements exactly the same interface as the regular database. So you could talk to one or the other, and your app doesn't know the difference. But obviously what happens when you read and write to one is very different, right? You read and write to the shard server, it figures out how to auto-balance and evenly distribute the data and distribute queries. The other one's just a regular database. But what's cool is your app doesn't know the difference or care, right? You just say this IP address versus that IP address, or this port versus that port. All right, so what we're going to do is we're going to look at an example. We're going to look at the United States weather data, because that's the data they used in this example. That was really excellent. So we're going to look at all of the weather data for the 20th century. Now this is an example taken from the MongoDB conference, which was in 2014. You can actually, I think there's a link right there to the video where they go into lots and lots of detail about this example for like an hour or something. But it turns out it's a ton of data, okay? And as you can imagine, we've had more data collected recently than in the past. We've had more machines and automatic things and internets and so on. But if you look at all the data throughout the years, right? This, by the way, is like 140 million per year up around here. We have 2.5 billion data points. And that's 4 terabytes of data. That's a significant amount of data. And each individual record is about 1.5K, 1.6K. Okay? So we're going to try to answer some interesting questions about this data, and we're going to do it on a regular database, regular non-sharded Mongo database, and we're going to do it on a sharded database, right? Okay, so here's what the records look like. I'll show you the C# version in a second. So there's some station ID. That means New York City, by the way, in case you're wondering where that one was. Here's the date in which it was recorded, and then it has these 2 sub-documents. One talks about the air temperature, what its value was in Celsius, and the quality, because they might have different levels of precision or something like that. And then atmospheric pressure. All right. So if we wanted to look at this in C#, right, remember these are kind of like straight up properties, and these curly braces mean other document or other object. So in C#, this would look like this. We'd have a class, which is a weather record, a public string, which we're calling ST for station ID. And this is something worth noting in MongoDB. See the name ST, TS, and air temperature? These are actually in the records. And because each record can actually be kind of the collection can be heterogeneous, you can have different types of records. They store these names in every single record, which is why they're using super short ones. Because if you have 2.5 billion of them and you add a few characters here, it makes a difference, right? Okay, so we've got this weather record. You see this is like regular data. It's got a date, time, and strain, and then it has a temp class here, which this is the temp class, and it has a pressure class here, which is the pressure class, which actually has basically the same thing, so you could do some object thing there, like inheritance, or just use the same type or something. But this is how it would look in C#, right? And you would query this thing from the database, and these would just come along for the ride. All right, so let's look at some setups we did. When I show you what this costs, you'll see that see why I borrowed their example and didn't set up my own. So here's one thing that we could do to try to set up this data and query it. So all these little numbers here, like I2, 8x large, these are actually virtual machine keys or names in EC2. So if you guys do anything with EC2, you can go and there's like a huge catalog of types of machines to choose from. These are literally the EC2 machines. If you wanted to like somehow replicate this, right, you could just go and look what that costs and go start one and so on. So we've got an application tier and a data tier. On the app tier, it's this super huge machine. Over here, also a relatively large machine with 251 gigs of RAM on one machine. That's already awesome, right? Like the cloud is just amazing. You go over there, you push a button, and poof, you have 251 gigs of RAM. Oh, and they hooked up a 6 terabyte SSD to it while they were at it. All right, and it probably took like 10 minutes or less, and that's pretty amazing. But so this is one possibility. Like this is the scale up. All right, we're going to scale up as much as we can, and this is probably like across the board the biggest, fastest thing you can buy that somehow doesn't use GPUs. So another possibility, excuse me, would be to use this sharding, and you'll see that we can get smaller disks, smaller servers, but more of them. All right, so over here is a possible scale out thing instead of trying to get a bigger and bigger machine. We would put the application tier over here on the same system, and we would have the Mongo S running locally, so the network latency is basically 0. Because there's very little effort that thing does. It's like just delegating across the network, more or less. Right? And then we have some MongoDBs. These are the actual servers that store the data. And the Mongo S's job is to automatically balance that and break it up and sort of fan out, scatter, gather the queries and so on. Now, notice how many of them there are. 100 of these guys. And each one of them has a 100 gigabyte SSD and 61 gigs of RAM. So taken cumulatively, we have 6.1 terabytes of RAM. That is a lot of RAM. It's like an unimaginable amount of RAM, to be honest. Like I can't even fathom it. And again, it's like these, multi-core sort of high-end machines. But they cost less, right? They're smaller. The disk is much smaller. The RAM is smaller. They cost less than the other ones. Okay? Now, we don't have to stop there. We can do more scale out. We can say, look, we could actually sort of have like a web farm type thing here. So we could scale out that end as well. So we have, let's say, 10 sort of web front ends. And each web front end has one of these sharding servers that is in sort of communication with everybody, right? They all know about this. Right? So we could sort of parallelize the queries going from here and from here to a little bit more. So what this basically means is everything is in RAM. right? We don't even have to use the disk. Back here, things are almost in, like SSD is almost RAM. Not quite, but it's close, yeah? Okay, so here we are. Now, let's ask some interesting questions. First of all, could you afford this? Is this a good idea, right? What does this cost? What do you guys think this costs? Any guesses? This is per year in EC2. It is not cheap. It's $60,000 a year for that one machine. You get no fault tolerance. You get very little upgradability while it's live and all these sorts of things. So you might need to have several of them. It's not cheap, but it is cheaper than $700,000. So maybe that 5 minutes of downtime per year is worth it. I don't know. I mean, it depends on what you're trying to do. So when I show you that this is faster, you'll be like, well, of course. But it comes with a cost. Not just this number, but also like it's more complicated to manage, right? Like this I can easily go and understand. This is hard to understand when I log into something, what is going on. Actually, MongoDB has this service that they offer called MMS, Mongo Management System or something like that, where you can go to EC2 and basically enter your account or your access secret key and your access ID or something like that, and say I would like a sharded cluster with each shard in a 3 replica set, and I'd want 5 of them on these types of machines. Go, and it'll automatically just do that for you. So this is like a feature that Mongo basically sells. MongoDB is free and open source. Like you can just go get it on. It's on GitHub. You could clone it if you wanted. So those are some of the types of ways they make some money on this stuff. All right. So first of all, they're both expensive, but one is dramatically more, like 10 times more, almost a little more. So let's ask some questions about performance. Right. So here's a graph. In all these graphs, they have the average time in milliseconds, the 95th percentile, like 95% of the time the queries happened with this time or lower, and then the 99th, right? So basically almost all the queries were faster than the red, whatever the red is in the graphs, yeah? And then we've got the single server, and we've got the cluster. So there's 2 things that you care about. One is response time, right? If every single query you take against the database takes a second, right? Even if nobody's on the machine, that's not a super good user experience, right? So you want the response time to be not too high, but you also might have a bunch of users, like if you're somebody like Facebook or Foursquare or somebody like that, all of whom use Mongo in some way or other, you need to be able to process a lot of requests, right? So down here we've got the actual number of requests per second that we can make where we're doing these queries. Right, so there's kind of like, you care maybe about one more than the other, depending on what you're doing. So the first thing we're going to do is we're going to do a query, and this is written in the native syntax, but imagine in your mind that this is link, right? Okay. So we're going to go find a station by ID. So what we're going to do is we're going to go to this one, whichever one that is. You guys remember which this one? I'm sure I don't remember. And we're going to say at exactly this time, I would like to know what the weather was. What the atmospheric pressure, what is the temperature, and I think that's all you can ask. Yeah? That's all that's in there. Okay, so we can say, go find this individual record, basically. And on the cluster, it took, let's say, about 0.75 milliseconds. 2.5 billion records. But even on the one super huge server, it was actually really fast. Right? It was almost the same time. It was longer, but almost the same time. And that's because the indexes fit in memory on both cases. So it's more or less, this record, whichever one you're asking for, lives on one of the 100 shards. The Mongo S knows where that is, and it says, go ask that server over there, which is actually smaller than this one. What is the date? What is the value? But this one has more data to look through, right? So there's kind of this balance. However, a whole bunch more people can ask the question of this cluster than they can of here, right? So we can do 40,000 requests per second, which is amazing on one machine. But here we do 600,000 requests per second, right? Within a millisecond, by the way, sub-millisecond, 600,000 of them per second. So that's kind of good, but $700,000, keep it in mind. All right, it's a trade-off. So this is cool, but you don't really see a great, like if your concern is latency, it doesn't really matter. If you're concerned with throughput, this is a good deal, right? You'll see in other places where it matters more. Okay, so what if I wanted to ask a more broad question? I want to know what the weather was for an entire year at one location. So I'm going to go to a different ID for the station ID, and I'm going to say I would like to go get where the time span is greater than this and less than this. So I want the weather of 1989, basically. Right, so that's got to sort of do a little more of a fan out type of thing. And it turns out when you fan out, you can go to the cluster and shoot this query to all 100 machines, and they can all individually do their work. Whereas this one doesn't get the ability to run on 100 machines in parallel, it just runs on the one still. And so this starts to make a big difference. So over here you can see this question gets answered in about 200 milliseconds, 300 milliseconds on the sharded cluster. And here it's 1.5 seconds. For one query, right? Like it's not just, it doesn't really matter how many you're doing. And you can't even ask it that many times. So 20 queries per second versus 430. Because that's a pretty serious amount of data. Right? So here the cluster starts to pay off in terms of latency. All right. Now, it gets more interesting when you think about the big data type of things. So far what we've seen is like the traditional relational database type question. Query this by this primary key, or where there's some sort of where clause that's pretty straightforward. So that's one thing that MongoDB supports. The other thing it supports is this what's called an aggregation framework. And the aggregation framework allows you to do what other databases do with map reduce. Or what you get to do is in the server, you get to sort of go through all the data, transform it, go through it again, transform it again, maybe take an average, use that average to ask another question, and sort of within the whole database, go through, analyze it a bunch, and then get an answer, either a number or a transformed set of records or something like that. Okay. Now, the syntax of this looks really nasty in its own language. If you look at the linked version, it's beautiful. I could actually show you that if you want to see it later, if we get time. I think we'll have some. So what we can do is say, I want to go and find every one of the 2.5 billion records where the air quality is either 1 or 5. And that means something to Noah. That means good. Don't know what else it means, right? But these are the ones that are reliable to us, basically. So we don't want to use unreliable data like, oh, it was really hot on this day, but we're actually unsure what the temperature was. That doesn't help us. So we need to find all the records that have reliable data, and then I would like to go through and group into the maximum temperature, right? Create a bunch of sort of subset, and then we're going to pull out from that series of maxes the highest one. Okay? So it turns out, sometime in the 20th century, it was 61.8 degrees Celsius, which is 143 degrees Fahrenheit. That's really hot. Do not want to be there. I don't know if that was Death Valley in California or the Middle East or somewhere, but it was hot. Now, if you're going to ask this question on that huge machine that cost $60,000, it would take you 4 hours and 45 minutes to figure that out. That's a while. If you did it on a sharded cluster, it would take you 2 minutes. What's really interesting about that is that's fast. But remember, we scaled out by a factor of 100. That's actually 142 times faster. So it's even faster than like the number of times that we scaled out, which I think is pretty interesting. If normally if you were to doing like threading or some other sort of performance thing, you said, well, this computational thing took a minute. Let's throw 10 threads at it. You'd be lucky if you got a 5x or 6x performance increase. Right? Like, you don't normally just, I doubled the number of processors, so I doubled the speed, sort of scale up. So this is really cool. But remember, it costs a lot more money. All right, so what do you guys think? Interesting? Yeah. You don't have to have 100 shards. You could have 5 or something, and it would still be a good deal. Like I showed you on the object rocket stuff, for like $150 a month, you get 5 sharded clusters with replication on SSDs. So this is a super extreme example, but these are things that are available to you, right, in non-trivial ways. Okay, so questions about the sharding stuff. I have a question for you. Let's go back for a minute. Here, this is sufficient. No, let's go back some more. Sorry. So, let's forget the replication. Let's say sharding versus one server. Which one is a more reliable system? Right? If I have one server and there's a 1% chance that that server dies and my database goes offline and I get woken up at 2 in the morning, the server's offline, coming to work. What's the chance that with 5 machines I'm going to get called? Unless I do something else. Some more reliable machines or whatever, right? How's it like, the relationship between like hardware breaking on these two things, it's got to be independent, right? Unless one like electrocutes another and they're near each other. So probabilistically speaking, independent events, some number of probability, it's number of times it could occur times the probability, right? So this is 5 times more likely to fail. So that means this one's 100 times more likely to fail. That's a problem, right? So, now it might not entirely fail all the way, or it might. It depends what your app's trying to answer. It could just lose some stuff, and that would be bad. So, really, when you think about this kind of stuff, you also need to somehow think about this sharding, right? And that's when, if you look at the object rocket thing, they say, here's your sharded cluster with this amount of replication. Right? So what a lot of people will do, take this back. What is the recommendation that people do is that each one of these elements in a shard should be one of those, right? Because what you get with these replica sets, what we'll talk about in a second, I'm deviating from the camera, I'm sorry. What you get is basically automatic failover in continuous sort of synchronization. Okay? We'll talk about a little bit of the details of it, but if one of these fails, it'll just like switch to another. Oh, that was a bad idea. I guess that one's gone. Let's go talk to another. And then there's an automatic way in which the die will come back to life and catch up and so on. All right. So that one over there is 5 times less likely to fail than a single server. This one is 5 times more likely to fail than a single server. But each one of these can be one of these replica sets. In which case you get a notification, hey, one of the replicas in here died, go change his hard drive, and then you would have no downtime. That kind of thing. Okay? So the recommendation is to use these in combination. And I think if you use the database as a service stuff, or if you use the MMS from MongoDB where they give you the management stuff, those are checkboxes and people probably just check them. Right? I mean, it costs more money, more hardware, whatever, but not tons. However, when I talk to people who are actually doing it, they're like, I know, it always starts, like, we have this sharded cluster and I know we should have replica sets, but we don't. And now can you help with this, right? So, just so you know, like, that's how it should be done, but I'm not sure what's happening in the industry. All right, so let's go talk about, go talk a little bit about this replication stuff, and then I'll stop so that we have time for questions. All right, so replication, right? Hopefully you feel like, well, if I have 100 server sharded cluster, now it's 100 times more likely to fail. I would like to add some durability back into the system. You care about replication. But that's not the only reason. There's all sorts of things that are interesting here. Now, these replica sets are built of 3 or more pieces, 3 or more servers. And the way it works, by default, is you can read and write to what's called the primary. And the primary is just a regular MongoDB, and it just happens to just do whatever it does. It's exactly the same as a single server, except for it keeps this thing called an op log, an operation log. And these guys basically tail that log, and that log contains every action done to the database. So there's a first and initial like synchronization, so they all have the database. As soon as somebody says, write this record, these guys read it and do that. As soon as somebody says, update this record, they read it and do that, right? So they're always in sync. But you can only read and write to this primary. So you get no faster performance in reading, you get no faster performance in writing, by default. Okay? But what you do get, that is super important, is you get strong consistency. Right? You don't get all the weirdness of like, well, I know I placed your order, but now I'm not sure anymore. Come back again, look, maybe, that's hard for programmers, right? So the default behavior for these replica sets is to be just for durability only. Right? That doesn't help for performance at all, but we can change that. Okay. So here's what this oplog thing looks like. Every time something happens to a record, basically that operation gets stored in this oplog. So here's an insert, and it says we inserted this thing with this ID and this data, right? And it's just the replica sets just go, okay, I'll do that too, right? They just sort of keep track of that. So here's a primary, somebody makes a change to it, it changes the actual data, and it also stashes this in the oplog, and all the other ones are reading that, right? And they could be really close to each other, like in the same rack, or one could be in Japan and still doing this, right? So one of the really good uses of this is for disaster recovery. Right? If you guys are working for like financial companies or somewhere where they're like, what happens if somebody flies a plane into our building? All of our databases are here. What do we do about it? Or in the less tragic case, what if it catches on fire and burns up, right? Not hopefully less tragic. So you need some way of saying, how are we getting our data to another place that we could recover from, right? So you could easily set something up like this, in another place. Right? All the financial companies in New York seem to have a place in New Jersey where they've got something like this, right? If you're in the cloud, you might have one of these in Ireland and one of these, somewhere else, right? At least a different availability zone, something to that effect. Okay. All right. So each one of these has a little heartbeat that goes around and around, and somebody's the primary. They go, "Hey, primary, you still there? Are you still there?" What's interesting is they all have to be able to see each other. It's not just like all the pieces need to be able to see the primary, but the others, replicas, have to all be able to see each other, because if this one dies, they need to know who's going to be the boss, and they have to have like a little chat about that. Right? So your network topography has to be set up so all the different replicas can see each other, basically. Okay. So what happens is, if maybe this one dies, they can't talk to it, there's like a 10-second timeout or 2 second, what did I say? A few seconds pass, and eventually they'll go, okay, you're dead, we've re-elected you. This one will come back and realize it's not the boss anymore. And these will, eventually, it might come back and become the primary, it might not. You can set up priorities, because like maybe one's on a high-end server with an SSD and one's on like a cheap machine in the corner. You don't want it to fail to the cheap machine in the corner and not go back to the fast one if it gets repaired, right? Okay, so when you connect to it, you need to set up your connection string to talk to not all of them, but a non-empty set of them. Because if the thing dies, if server one dies, even though it was the primary originally, you would like your app just go, I'll just find the other one. Right? As soon as it finds one, it'll find all of them that are working still. But you want to give it a couple of options to go look for. Otherwise, the failover doesn't really work. This is the one thing that you have to do in your app that's kind of like, I know whether or not I'm doing scale out replication type of stuff or not. Okay? So, speaking of scale out, you can go and say, I could talk to the primary, or you can say, look, I would actually rather have all of my web roles that are doing stuff on sort of the front page or things that are kind of static read from secondaries. Okay? And that way the primary that's doing the writes and maybe is the most fresh doesn't take very much traffic at all. And you could have 20 replicas. You could be reading from 19 of them, and the one would still be super responsive. However, that introduces eventual consistency, which is not so fun. So you can say things like prefer primary, prefer secondary, or nearest for geolocation. You guys know how they measure distance? Not by IP address. Ping time. So whatever one has the lowest ping time, which is hopefully the one in the same data center, unless something's really wrong with it, it would automatically find that one and use it. Right? So you would use this for like geoscale. Okay, you can specify this, here's the C# stuff, you can specify this in the connection string or on a per query basis. Now, if you go down this path, you end up in some possible situations. By default, MongoDB, even in the sharded cluster, even in the regular replica sets, has strict consistency. It is a good thing. That means it's like SQL Server. You don't have to think about whether or not once it said it was written or not, right? It's the way that normal databases work. And if you just go over here and say read from secondary and don't think about it, you land in this world of eventual consistency. Because it goes like this. No matter what, you can only write to the primary. That's the rules, right? Not all sort of replica cluster type of databases work that way, but Mongo does. So suppose I write, let me go back to a picture I can point at. Actually, the picture is a little more forward. Yeah. So suppose I write here and then immediately go read here. You might think, well, how likely is that? It's very likely. Let's think of like Amazon.com. I'm going to write a review. I go over there and I read this book and it was amazing. It changed my life. I'm going to like write the biggest review I've ever written. So I go down to the section when they have reviews, 5 stars. This was amazing. 2 hours later, I hit save. Immediately post back to the server, redirect, refresh, boom. But maybe that second request hits this one faster than it was able to replicate. My post is gone. I'm like, no, I'm never reviewing a book again. I hate this place, right? And then you refresh it a little bit later, and hey, it's back. Or maybe you write it again and you hit save, and now there's 2 of them, which is even worse, right? So that's the whole problem you hit with eventual consistency. Like I said, by default, if you don't change anything, you don't have that problem. But you don't get any performance help either. Right? Trade-off. So you could say, I would like to write to the primary, but read from one of the secondaries so that I'm basically scaling reads. And if you have a read-heavy application, that's super important, as long as you don't have so much data it doesn't fit onto the computer. So this is helpful, but it has this problem of eventual consistency that I just described. Now, there's different levels of tolerance for consistency. One level of tolerance is, I tell my friend, go, I'm just about to press save, like I'm gonna press save, now go review my review right now, right? And maybe if you, like in a separate request, when it made it to that server, you might see things out of sync, right? It might take a few milliseconds or half a second or something before everything syncs up across the world. That probably isn't a problem, but if you make a change and you don't see the change, that's a huge problem, right? So there's a solution for that, right? There's like what I call read my rights consistency. If I submit something in a web form, I want to see that that is saved. If I make a change in my app, I want to see that that is saved. If somebody else happens to view it at the exact same time, whether or not they see that change, I don't care. If they refresh a second later, they'll see it. So that's what I call read my rights consistency. And you can use this thing called a write concern to add read my rights consistency to replica sets. So what you can say is, I want to write here, and do not tell me that it's written. Just pretend, don't return from the function save until you have written it to 3 servers. And if you only have 3 servers, it's 100% consistent by the time that's counted as saved. Right? By the time the page refreshes, it doesn't matter which server it goes to, because it's already been written to all of them. Make sense? So you can use this setting, but again, trade-offs. So what if one of these dies, and then I say, wait until 3 of them are written to? I'm gonna wait a while, right? It's gonna crash and say, could not write data, or time out, or something like that, because I said wait until 3, and there's only now 2, right? So you decrease the reliability, but you sort of increase the scale. Make sense? All right. So an interesting thing you can do, a couple other things you can do. Here's the write concerns. You can say, I don't even want to wait for the network to connect. Just good luck, off it goes. Or you can say, just wait until I got the network socket open and accepted, and then forget it. Right? These are kind of fire and forget style. Like maybe you're doing logging and you don't care. You want your app to just go as fast as it can. The default is acknowledge, wait for primary, but you can also say wait for like a majority, wait for the ones that are tagged with like my location, or things like that. All right. So you can do this in C#, and you can set the write concern, majority, unacknowledged, things like that. All right, so another really interesting use of replica sets is for what I call non-core services. One of those is the backup that I talked about, right? Your disaster recovery stuff. So you can put a replica into this set and say, this thing is a hidden replica here. And what that means is it can never become primary. If somebody's reading from the secondary, they'll never find their way there, right? It's not meant to be participating in the app, but you want this server to be in synchronization with all the other servers continuously, right? So you can put this one in the Germany data center, and these can live in the Ireland data center. And if the Ireland data center goes down, we're still sort of good. We're less bad off. How's that? And then you can do things like run various commands against this. Like you could say dump, which is one of the ways you do backup. However, if you've got a huge amount of data and you run MongoDB, it can like seriously slow down your server or your cluster, right? So you want to like push that to something that's not really processing requests and then run it on there. There's other options as well for this kind of backup, but that's one use. The other is if I want to do like big data stuff. I want to ask that question, like that question that took a minute to answer during the aggregation framework or something. But I don't want the execution of those queries to slow down my actual live website, right? Suppose I'm like one of the largest retailers in the country who happens to have run their e-commerce system through MongoDB and wanted to ask a bunch of questions about it. Maybe they would want to push this over to another machine so they could run these queries that might bog down the server on Cyber Monday or something like that when all the shopping is happening, but they don't actually want the shopping to stop. You know, that's a reasonable expectation. So you could have like this analytics server that you could talk to over here. And that would all basically be live data because it's only a few milliseconds delayed from the primary. Right, so there's a lot of interesting uses. So this is not a traditional scale out in the sense of, if I'm reading and writing from the primary, this thing's not any faster. But because I could push off all the extra and let it just be purely dedicated to the app and not backup, not analytics, not that kind of stuff, it would in effect make it go faster, right? So here's another sort of scale out type thing you can do.
If you build the analytics replica it off, isn't that replica could have different indexing structures or see on a more database?
I don't believe you can have different indexes. Like it would be reasonable to say I want way more indexes there.
Yes, that's the
right. I want almost maybe no indexes on that.
Although what you could do, I suppose, is off the backup you could generate a second data.
Yes.
So pull the data off,
yes.
Generate your new indexes from that.
Yeah, absolutely. Or even write like that op log.
Yeah.
That is available to you as well, theoretically. It's not supposed to be, but you could go look at it and create your own version
of the data.
And then you just apply a reaction, but then the thing you're applying the action to has way more indexes. It's not officially supported. They say they're like, you're not supposed to tail the op log. He's like, we have to do it. I'm sorry. Forgive me. All right. Questions, comments? All right. Cool. So there's a lot of interesting stuff you guys can do here with this. All right. So that's close to everything I have to talk about, but I will show you a few other things. So, maybe one of the first things to do is think about what is the right kind of database that you're going to work with. I think, and the MongoDB people believe they are building a very general database. I think MongoDB can be the database that you use. It's not like I have to have SQL and then I kind of, copy it over to Mongo. It's like good enough to be the database. Right, but it is not necessarily the database for every problem, right? But it's not to say it should become a hammer necessarily, right? So if you've got like highly relational stuff, maybe a graph database is better. It doesn't scale, it can be so much faster, it doesn't matter. Question?
I'm working on .NET. I've been working in Java with MongoDB before. But can you say something about the drivers for .NET to MongoDB?
Sure, I'll say, so the question is, just for the camera, is you're working with the Java drivers.
I have been working with that.
You have been, and the question is, what's it like to do something in MongoDB to work with it there, right?
And in .NET.
In .NET, yeah, exactly. Sorry, in .NET. So MongoDB has a bunch of good drivers, and I think that's one of the really big value propositions is it's got a great Java driver. Are you using the asynchronous one or the regular one?
Asynchronous.
Yeah, okay. That's nice. The .NET one is not yet asynchronous, but it will be in a few in a month or something like that. So they've got a great one for Java, a great one for Node.js. They've got a great one for .NET, Python. They've got probably like 20 or 30 platforms or languages they support. Let me show you what it kind of looks like in .NET. Okay. So, Mark, didn't I say I didn't need this? So give me until that progress bar is across. So welcome to Windows 10. All right. So if we go over here, here's a standard C# program, and because my fonts are all funky, let's do that. So this is the using, all right. So here's what the main primary way of working with MongoDB from .NET looks like. So here's a users collection. Let me find one with the books collection. Users, books. These are not super interesting queries. They're pretty straightforward. So there's 3 tables in this, like this book one that I showed you with the performance. One is publishers, one is books with the reviews in the books table, and then one is the users table. So here we're going to go to the publishers table, and we're going to do a query and find the one and only publisher that is Second Avenue Publishing. So this line of code right here, whoops. That line of code right there goes to the database and does that query. And the way that looks in the JavaScript level would be db.publishers.find, and then it would say name : whatever that is. Sorry, parentheses as well. My comment doesn't compile yet. There we go. Okay, so it basically takes the link expression, which is, looks like an in-memory language level thing, and it translates it to the native query syntax. And obviously, because it lands in the native query syntax, it uses the indexes and all of those kinds of things, right? So let's look at some more over here. Yeah, this is the same one. So let me find something more interesting. I'll open up our developmental website, and I'll show you some more standard queries. So while that's loading, so you go over here, like to develop.com, which is slow on the Wi-Fi apparently, and you go over here and say like .NET. I want all the .NET classes. Show me, the modern ASP.NET class, right? Like all those are Mongo queries. So what does that look like? Let's try this. Right, so these are the types of things you would write, right? So trying to find a course given something, an engagement that maybe somebody's going to go to. So you might write code like this, and this is pretty interesting. So I'm going to go and do a look, not at the document, but a sub-document within an array. All right, so let's look at how that looks. So here, this class has a list of these engagement objects, right? If you look at the engagement objects, they've got a public ID and they've got other types of stuff. And you can see you can control the serialization with these attributes and say, serialize this locally, don't serialize this at all, because it'll create a cycle and so on. Okay, so the query that you write to actually go get that is you say, go to that set of courses and give me the one item that you're going to find or null, where it's the case that the list has any record that matches the ID I'm looking for. Does that make sense? And you're going to go through there, and that's like 1 millisecond or or less, right? As you know, because you've been working with it in Java, it shouldn't be any different. But the point is, it becomes the actual db.courses.find statement that if you ask a Mongo expert to write, they would write the same thing that this link transfers into. Does that make sense? Now, the thing that's coming, for those of you guys who are, how many of you know what async and await is? You familiar with this? Oh, Mark does. Async and await is amazing. And so what's coming in the next version of MongoDB, the driver, is I can put the word async here, which means that will now run on another thread on an IO completion port that doesn't even take CPU work. And I can then go up here and write things like await here, async here, and then you can go through your entire tier all the way from the web tier down to the database and like basically do what Node.js does to parallelize it. Push everything to a callback on an async IO port, except for because it's .NET and it's awesome, you don't have to write code as if it were doing that, right? It's really fantastic. So that's coming in the next version of the driver, which is in beta right now, I believe. So those guys move fast. The other thing, to speak of drivers, that's worth talking about, if I go log into GitHub,
This driver will be delivered.
when?
When can we expect
This is a good question.
driver?
So it's the new server 3.0 just came out. The new driver, I don't know, but see this guy, Craig Wilson? You can see him working away on it right here. And they already, you can go over here and you can see where's their releases. Dun, 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 dun. Somewhere to, what happened to the order in here? Those are not proper releases. Somewhere in here, they were just releasing the beta, so I'm not sure where it is. Oh, I probably am, it's the wrong one. I need to go to MongoDB master and find it for the release. But if you just go to their GitHub stuff, you can see like it's just full of them doing their stuff, and this is where they do their work, and so you can track it pretty easily. You could go contact Craig and say, hey Craig, what's going on? There's like 3 or 4 guys, Craig Wilson, Robert Stamm, and a few other guys whose job it is to do the .NET layer. There's a couple of guys, 2 or 3 guys whose pure full-time job is to do the Java layer, and there's a couple of guys that do the Python layer, right? So on. So, other questions, comments? I've got a few more minutes. Yes. Sorry, you're next.
With the link syntax, is there a way to find out what it's compiled down to JSON syntax in the same way you could like with the
That is a very good question. It would be awesome if somebody wrote like a GitHub package and a NuGet package that would tell you that, right?
So the answer is no.
No, the answer is, the answer is right here. I wrote one. So I'll show you where this is, but you can go over here, like, let me zoom this in for you. So if I got a query like this, query from P and Mongo people where the age is this and the length is that, order by, right, all that. You can go and install this thing. I'll show you where it is, right? It's on NuGet, so you can just go to NuGet in Visual Studio and say, add this as a NuGet package. And then you can just say two Mongo query syntax on the link expression. And it will write this.
Has a SQL one as well, isn't there? I saw a couple of weeks back. Can't remember who it is by.
One that'll convert it to what SQL would be?
She essentially writes the SQL and it interprets it to JSON.
Oh, interesting, yeah.
Which is quite nice if you
Yes.
write JSON and you're used to writing SQL.
Yeah, I think I know what you're talking about. That is really nice. So this library actually does 2 things. One, it says let you say to Mongo query syntax, and you can copy that to somewhere like RoboMongo or somewhere and try it. So you can get your app out of the way and just purely do it in the console, right? The other one is you can do an explained, you say explain this to me, like what is this doing? It'll tell you whether or not, it'll tell you all this stuff, like whether or not it's using an index. If you see a cursor, that is bad. Just cursor, sorry, not cursor, if you see, what is it called? Basic cursor, I think is here, right, under cursor. If it doesn't have something that looks like a B-tree cursor, it's not an index and that's a problem. Maybe, I mean, not everything should be an index, but yes.
It looks like most of the examples you've had so far more cover scaling for reads. How does Mongo scale for writes?
So that's the question is, how well does MongoDB scale for writes? until version 3 of MongoDB. And if you upgrade an old version if you basically upgrade the server and you've got an existing database, it will not be upgraded. So this applies to that as well, unless you like run a little operation to do the upgrade on your files. They've recently added this thing called Wireshark. It's this company they bought I think that came from Berkeley DB. And apparently it's a much better format for the way the files are written on disk. And so they say version 3 of the database is supposed to be 7 to 10 times faster than version 2.8. Right, so the version that's out a month ago is 10 times slower than the version that it came out like a few weeks ago. So with that in mind, the slow version is 15 times faster than SQL Server. Yeah? And on a single server, if you do sharding, it's multiplied by the number of shards to some degree. I mean, it depends how big is your data, what is your hard drive, all those things. But the tests, like when we were teaching that class together, Mark and Ike was there, all the tests that we've been able to do, it's around 15 times faster than ADO.NET and faster still than Entity Framework, because Entity Framework has overhead over ADO.NET. So it's definitely faster, and that's where things like the sharding stuff let you multiply that, like basically until it's fast enough. So just to give you a sense of like how much data, how much faster does it need to be? It depends on what you're doing. But I did some work with one of the largest retailers in the world during their Cyber Monday sort of, in the US we have this ridiculous sort of thing people do every year where after Thanksgiving they just go shop and spend all their money they've saved up all year. And so we have a thing called Black Friday where everybody goes, there's big sales and they go shopping. And on Monday they call Cyber Monday where everybody shops online. And so they called me up and they said, we are super concerned that our server will not take Cyber Monday. I said, okay. And so I talked to them for a little while about what they could do. And they had a 10 shard cluster with no replication. But it was more for the analytics they were collecting. And then they said, actually it was like super boring. The CPUs were like at 1%, it was nothing. And they only had 10, right? And that was like one of the largest traffic days for them. So chances are your system could take it as well with that, but it depends, right? It's hard to come up with, I guess what I would say is figure out what you're trying to do and try to do some tests on that, because it really depends on what you're trying to do, if it will help you or whatever. But generally it's significantly faster. It's not slower, I'll tell you that for sure.
Well, I'm kind of trying to compare it to Cassandra, because that seems to be the next best choice.
Sure. So Cassandra and some of these other ones, they're also really good, and I think they actually scale better, but they're way more complicated. Like setting this up is, you can set up one server, 10 minutes later you're done and the thing is configured. With Cassandra and Hadoop and some of these things, you've got like 7 or 8 pieces that are all trying to do their thing. And I don't know that much about Cassandra, but I know there's more to it, right? With like these sort of things that are doing, monitoring the clusters for failover and stuff like that. So give it a try. How's that? Yeah? Other questions, comments? Got a few minutes. All right, so let me show you some other stuff if you don't have questions. Let's look at this little app that I got put together for you, which is hiding here. So I told you should do things to make your app faster on a single server before you think about adding a whole bunch of network topography and managing multiple machines and all that junk, right? So let me show you an example here. Remember that bookstore app, right? 271,000 books, 1.2 million reviews of those 270,000 books. Here's a little app that we put together for our MongoDB class. And what it does is it asks some basic questions about that data set. And first it asks them without indexes, and then it asks them with indexes. But it doesn't just go and say, well, let me add an index and see if it's fast or slow. It actually goes and it turns on profiling inside of MongoDB and says, I'm gonna ask a bunch of questions. MongoDB, tell me what is the worst question I have asked? Like, what is the slowest thing? What is the second slowest thing? What is the third slowest thing I've done? Now let's try to like optimize those. Maybe with document redesign, maybe just by adding indexes, right? So I'll run it for you. It's running. Now you can see, here it goes. So it's running, and it reset the profiling, it dropped all the indexes from the databases. Now it's asking a bunch of questions, and it says, okay, these are all the queries in there that took more than 5 milliseconds. Now, for those of you who are not using MongoDB, would you go about like worrying about stuff that took 10 milliseconds on your SQL server? No, you're like, I didn't have to go to lunch, it's good, you know? So these are the ones that are really bad. They took more than 5 milliseconds on our 1.2 million records. So these are actually the queries that came out, right? This is the collection, this is the query, this is how long it took. So what it's gonna do now is it's gonna take these and it's gonna add indexes. Actually, first it's answering the questions that it was trying to ask. It says, okay, one of the questions was how many of the users who reviewed one or more of the books are 18 years old? 3,703 of them. And it used, whoops, sorry about that, it used basic cursor, that's bad. And it took not too long actually to answer these questions. Well, you know, depends what's real. Like, I could do it in 1 millisecond or I could do it in 300. Like, is that, how bad is that? I don't know, right? So these are, I don't know, I would consider these not great. How many books are published by this group, which is, what is that over there? Oh no, that's just getting the books or something. There are 99 users who live in Moscow, that many seconds. So you can see right now it's adding the indexes, and it has been for a while. You can add indexes in the background, or you can add them and block your server until it's done. That's something you can consider. So then it reset the profiling, and it says, all right, let's ask that question again. Here are the ones that took more than 5 milliseconds. Empty set. Right? The queries in the system that took more than 5 milliseconds, there are none. That's super awesome. Okay, so let's see. How many users, or how many people are 18-year-old? 1 millisecond. How many people live in Calgary? 127,000 of them. 0 milliseconds. This one, because we were pulling something back, the response time was was like fast enough, but the actual streaming of them back took longer. So 31 milliseconds. Similarly here to read them back. Number of users live in Moscow, 0, right? So those are like more than 200 times faster. Right? They weren't terrible before, but now they're like, you know, don't even think about it, right? Why would you have caching in this application anymore? If you had caching, you would be doing it wrong, unless you just want like failover or something, because it's as fast as the cache would be basically, and you don't need that overhead, right? So,
do you get any degradation in terms of the write performance? Traditionally, it would be a fine balance between your indexing strategy that.
sure, yeah. So,
the slower the write performance and the faster the read performance.
I mean, you saw how long it took to add those indexes.
So, but is
So-
Mongo essentially saying, well, we write so fast, and we actually it's kind of almost.
The bigger, the more data you have,
Yeah.
the more, and the more indexes you have, the slower, especially the more indexes you have, the slower the writes are going to be. So yeah, there's definitely a trade-off here. And one of the things the guys were considering in this e-commerce place was if it can't keep up with the load, we're going to drop all the indexes.
Right.
So we can no longer answer big data questions, but we'll actually save the data and we'll turn it on at night or something. Put the indexes back. Something to that effect. That make sense? So yeah, it is a very strong correlation between speed and indexes. There's always an index on the primary key and there's no others. Let me just show you maybe really quick. Oops, wrong button, there we go. How you add the indexes. Enable profiling. Well, first of all, how do you enable profiling? You say, set profiling none. You drop the database. That's how you reset it. And then you go back and you turn it back on and say, set profiling. Anything that's slow versus every query and slow milliseconds, we said that was 10 milliseconds. And then to add, where is here's our add indexes. So here's how you add an index. You would go to the books collection, and say ensure index, and this actually goes, here's the one that you saw before, go into that ratings array, which has a set of objects. That one property of those nested objects are the user ID, right? So that's the one that let it answer that question super fast. Right. So you should definitely do this before you're like, oh, I gotta go buy 10 machines in EC2, right? Do this first, this is super easy. Turn on profiling, run your app for a while, see what's slow, add some indexes. And if you look at like our website over here, whoa, don't do that, that's gonna be bad. All right, hold on, what do I want? Mongo config, I think it is, yeah. This is part of our ASP.NET startup process, right? And it just does ensure index. And if the index already exists, it just goes, yeah, whatever, we got that, thank you. And if it doesn't exist, it creates it. So we've got our stuff hosted in EC2, and there's a Mongo server that it talks to, and we might make these changes locally. We don't have to like log into the Mongo server and say, hey, Mongo server, now you're gonna need a new index in production and there. We just write our app, so like whatever Mongo server it talks to, it just sort of synchronizes the indexes. Right, so I push a button to publish it to EC2 through Visual Studio, and then at startup, basically it generates the indexes. But that's because our indexes can generate, if it were empty, in like 2 or 3 seconds. If you had so much data it took an hour to generate the index, that might not be a recommended idea. Just like, depends on what you're doing, but this is really helpful if you have small enough data.
Does the same thing apply to collections?
Um,
You just have the app created on the fly?
So that's a really good question, and it's actually, there's a lot of techniques. So the question is like, how can I do that with collections and change their structure more or less? If you search for this, C# serialization MongoDB, you will actually be quite pleasantly surprised what you find, I believe. Serializing documents with C# driver. Wait for it. Look at the size of that scroll bar. Like, there are a lot of options on how you can control the serialization. There's like layer upon layer. There's attributes, there's automatic stuff, there's like classes that will actually do the serialization. You can control it there. There's all kinds of things you can do. If you're adding fields, you don't have to do anything. It'll automatically just like start working for the most part. If you're deleting a field, it will crash unless you say, it's okay that I deleted that field, add in the C# layer. In which you can add like a bson ignore extra elements. If you add that, it won't crash. Because basically, if you take a class and you load it up and it doesn't have a place to put all the data, if you were to call save on that, you would wipe away what was there before, right? So they won't let you do that by default because it's dangerous. But if you say this, you're like, I mean to do that, just out of my way. So what we do actually a lot of times is, if we make a change to the structure, we'll just change the class, and then we'll go write some script that will just load and save every document. And then it basically reshapes it, and then we'd go back and we would take this back off so that it doesn't happen accidentally later. The other reason is, if you write a link query and maybe the default value is 0 of some like integer or something, which it would be, right, possibly, and you write a link query against that field where you say it's greater than or equal to 0, you would expect some number of records to come back. But if that thing doesn't even exist in some of the records, you might get a different result than what in memory it would look like. So that resave is kind of like, so stuff that happens at the database is kind of always what you expect. But it's not often we have to do that. Usually we're adding a field rather than changing or taking away a field. Right? Usually like, oh, I need more data on here, just throw it in. It's not always true, but. And I just use LinkPad for that. You know LinkPad? You can hook LinkPad into MongoDB, all gonna go. All right, I think that is about it for time. So let's see, I probably have one quick summary thing to say or whatever, let's see. Yeah, so I think, there's a couple of things to think about in terms of scaling. Make sure your app is fast on a single server, as fast as it can be. That has to do with document design and indexes. And then look into scaling out with sharding. Keep in mind the reliability. You might want to add replica sets. Also, just launched a podcast, Talk Python to Me. You guys are like, I don't care about Python. Why are you telling me this? One of the first or second guests will be one of the guys from MongoDB who is in charge of the Python stuff. So might be interesting conversations there. And if you want training, I work with development, we kind of do that kind of stuff. So just let me know. All right, so thank you so much for coming. And I will stay after if you have any questions.